Hi, and welcome to Econ 480. These videos were recorded while I taught the class over Zoom, but they were edited so that the student faces, their questions, and my answers to those questions do not appear. As a result, these videos are going to be shorter than a normal lecture and then may have unnatural transitions. But I hope you enjoy them anyway. Bye now. All right, so I think we're ready. This is lecture 5. Today we're going to talk about more on endogeneity that we started talking a couple of lectures ago. So, again, to recap and see where we are, so far we talk about IB, the problem of endogeneity, the introduction of these instruments of IB to solve the problem of endogeneity. And then we discuss the Iv estimator, the two-stage least squares estimator, and their properties, essentially consistency and asymptotic normality. Where in asymptotic normality, we learned that these estimators are asymptotically normal with the variance covariance matrix that we denoted by B. And we also talk about how to estimate that last class. So today we're going to sort of like change gears, and we are going to have a lecture that is split in 3 parts that are rather I'll say, independent of each other. We're going to first talk about the efficiency of two-stage least squares. We're going to show, and we had some conversations last class coming from questions about whether doing two-stage least squares made sense relative to other possible linear combinations. We're going to answer that question under some conditions. And then we're going to talk about the so-called weak instruments or weak IVs and discuss what the problem is. And finally, we're going to talk about the local average treatment effect, or there is late, which is an interpretation of the Iv estimate in the case with heterogeneous effects. So let's get started. So the setting that we're going to consider is the same one that we had last class. I'm not going to read all this again, but it's just y equals x beta plus u. And we're going to assume that the instrument is exogenous. Expected value of ZU is 0. That the expected value of ZX prime is finite. This expectation is well defined. The expected value of ZZ prime is finite. Again, this expectation is well defined. There's no perfect collinearity in Z, which eventually gives us that this variance or this matrix over here is invertible. And then the rank of expected value of Zx prime is k plus 1, which we learned last class that this gives us that the projection of Z on X as a projection matrix that is full rank as well. So we're going to assume today we have a random sample of size n from the distribution of x, y, z. And then the two-stage least squares estimator identifies beta, as we saw, by means of the projection matrix pi. So today we're going to be talking about why this particular matrix pi is the one that we use to weight the instruments. So if you remember, last class we defined this x hat, which was pi prime z, and we said two-stage least squares is IB with x hat as an instrument. So we're just doing instrumental variables where we first take a particular linear combination of instruments. And so what we want to say today, or ask ourselves today, is this a good linear combination? And that's what this first part is going to be about. So we're going to start by noticing that in principle, we could use any matrix that is L plus 1 times K plus 1 dimensional. I'm going to call this matrix capital gamma, such that expected value of gamma prime Z X prime has full rank. So if you remember when we cover IB last time, or two-stage least squares, we said, look, we have expected value of ZY equals expected value of Z prime. Oh my God. Sorry again. Expected value of Cx prime beta. And so what we did was we pre-multiply by this matrix pi on both sides. And by doing this, we obtain a matrix here on the right-hand side that was invertible. Okay, but as I write over here, we could have pre-multiplied by any other matrix. Here, let's call it gamma. And as long as that matrix was such that this guy is invertible, we could have obtained a different representation. So in general, it would have led to something that looks like this. Beta is equal to this expression where instead of having pi, we have gamma. This is a different representation of beta. So we learned that beta could be identified through different such matrices. And then if this is the representation that we have, this would have led to an estimator that would have looked like this. Let me call it beta tilde n. It's just 1 over n, the sum of gamma prime zx prime inverse. 1 over n sum of gamma prime zi yi. And if this matrix gamma was not was unknown, but you could estimate it. So as long as you had a consistent estimator that we can call gamma hat n, then essentially the same analysis we did the previous class would have applied to this case. And in particular, we would have obtained that this estimator beta tilde is consistent under these assumptions, and it is asymptotically normal. Now, it is asymptotically normal, but it will have an asymptotic variance that is not going to be the same as the one that we obtained for the two-stage least squares estimator. And so let's discuss that. Suppose that the variance of ZU is finite. This is the same assumption we used before. Then in this case, we have that square root n beta tilde minus beta conversion distribution to a normal with mean 0 and variance b tilde, okay, where b tilde is this expression over here. Again, it takes a sandwich form as before. And instead of including these pipes floating around, it now has this gamma. So what we want to show now is that under some conditions or some assumptions that I'm going to describe next, the best choice of gamma is given by pi. Okay? And that means that this matrix over here, B tilde, is at least as big as the same matrix that we obtain when we do two stages least squares. And we're going to show that. And in order to show that, we're going to impose these two additional assumptions. The expected value of u conditional z is 0, and the variance of u conditional z is sigma squared. So, in other words, these are assuming or introducing homogeneity. So, in addition, I want to introduce this notation. W star is just going to be pi prime z, and W is just going to be gamma prime z. And what we want to show is this inequality that we have over here. I'm going to start by rewriting this matrix B tilde using our homogeneity assumption. So let me do that. So B tilde here is going to be sigma square times expected value of gamma prime zx prime inverse gamma prime expected value of z prime gamma expected value of gamma prime dx prime inverse prime. And I'm going to say recall that x was phi prime z plus b with expected value of z b prime being 0. So what this means is that the expected value of z prime you can write as expected value of z prime phi. And I'm going to use this again. We used this before last week in the proof of two-stage least squares. Let's use it here. So I'm going to have sigma square expected value of gamma prime dz prime phi. Let me take these gammas inside the expectation here. So I'm going to have expected value of gamma z prime gamma. And let's do the same trick here in the last term. So this is C prime, okay, inverse prime. And so now notice that this object over here is what I called W earlier. This one over here is W star prime. And then you can do the same with the other ones. This is W, W prime, W, W star prime. So we can finally write this in the following way, just to have a shorter expression. Effective value of W, W star inverse, effective value of W, W prime, effective value of W prime, this is not W prime, just W, W star prime, inverse prime. And here we obtain a representation of this matrix B tilde that it's going to be useful for our next derivation. I'm going to say here, note, when gamma equals pi, that is when we just do two station least squares, this equals sigma square times expected value of W star prime inverse. In the case of two station least squares, this is exactly the limiting variance in that case. Okay, so we want to prove, again, the B tilde is at least as big as B, which we re-express here in this way. And now we have these two expressions that are convenient. So here I just rewrote the last derivation that we had. And notice that I'm going to say we want to prove that B is less than or equal than B tilde. You can rewrite this as B inverse greater than or equal than B tilde inverse. Or, just take this to the other side. The difference between B inverse and B tilde inference is greater than or equal to 0. So the advantage of working with the inverses here is that it just simplifies expressions. So notice that I don't need sigma square for these arguments. So I'm going to write this difference is expected value of W star prime inverse. This is B inverse. And now I'm going to subtract B tilde inverse, which is expected value of W star prime, expected value of W prime inverse, expected value of W star prime. And then turns out that this entire expression equals the expected value of W hat star times W hat star prime. So it's the expected value of random matrix, random back time itself. And so this is greater than or equal to 0 by definition. Now, what is this W hat? Well, W hat star is simply the W star minus the best linear prediction of W star given W. So we can write it W star minus the best linear predictor W star given W. And this is just going to be W star minus expected value of W star prime, expected value W prime inverse W, and do some algebra. So all you have to do here, and this is the step that I'm going to skip, just take this definition of W hat star, just compute this expectation. You're going to have some terms that are going to cancel out. And then this is going to be equal exactly to this expression that we want. So as a result, then we have that B is less than or equal than B tilde. And so two-stage least squares is efficient, or I should say asymptotically efficient, but I'm going to be using just the word efficient under strong assumptions. Mainly, these strong assumptions are the expected value of u given z is 0, then the variance of u squared. So, which are the assumptions that gives us homogeneity. So, in this case, we assume that model is stochastic, and it turns out that the weights that you obtain, or the weights that are used by two-stage least squares, the particular linear combination that two-stage least squares take are um, are um, are the best linear combination in this particular sense. Yes. Okay, that's actually a good question. So it's true. Like, you suppose that C here is just Z1 and C2. So you have two instruments, a one endogenous variable. So you can just say, I'll use two, or you just or use this instrument separately. So then if you define the first linear combination gamma 1 of Z as the one that picks the first instrument, and the second one as the one that picks the second instrument, then this result is saying that under these assumptions again, you are better off in terms of asymptotic efficiency by using both instruments as opposed to using each of the instruments separately in separate IB um, regressions. Okay. Any other questions about this first part? All right, so let's keep going. So now we're going to talk about weak instruments or weak IB. So this this is what's going on in this case. We have in the previous results, last class, and throughout this course actually, and have estimators that are asymptotically normal. In particular, the two-stage least squares estimator, the IB estimator is asymptotically normal under conditions, and we're going to use these normal approximations to do testing to do confidence interval. One problem I wrote here is that the normal approximation can be poor in finite samples when the rank of expected value of zx prime is close to being deficient. And so if you just think in terms of the scalar case, what we're saying is the correlation between the instrument and the endogenous variable is small, okay? And so what we're going to talk about today, what is small? What does it mean small? The consequences is that, as I said, if hypothesis tests that are based off the normal approximation and confidence regions or intervals that are based off on normal approximation are going to behave poorly. So you're going to be forming, say, a 95% confidence interval with the expectation that your confidence interval is going to cover the truth 95% of the time. But you're having this problem where the finite sample distribution doesn't look like anything, well, doesn't look like a standard normal. And so you're going to be covering your truth parameter with 70% of the time, 60% of the time. Could even be worse. Okay. So the problem with weak instruments, and the reason why typically it is an advanced topic, not a topic that you would include in a first year class, is that in order to do a proper analysis, it requires to do asymptotics in which you let certain parameters to move with the sample size. Okay. And in particular, when you talk about the rank of this matrix, or, you can just think about the covariance between X and Z scalar case, we want to do asymptotics in which this covariance is getting smaller and smaller as the sample size increases. And again, in order to understand that well, you need to introduce tools that I'm not covering in this class. So what I'm going to do instead is I'm going to illustrate the problem in the context of a very simple, stylized, and simple example. And hopefully we're going to get all the intuition of what this problem is about without getting into the technicalities of the problem. So consider this example. We're going to consider the case where we have an outcome, an endogenous variable. There's no constant term in this model. Notice just y equals x beta plus u. And then there's an instrument. And again, no even constant term here. We're going to add two assumptions that deviate from what we normally do. The first one is that z's are going to be non-stochastic, non-random. And this is going to be, again, all for simplicity. The second one is that the joint distribution of u and b is just going to be normal with some variance covariance matrix. And so I'm going to be exploiting these two simplifications to do a derivation that is simple. Then, assuming that pi is different than 0, again, remember pi in this model is over here. You can have the Iv estimator, which is this guy that I wrote over here. Notice that you can rewrite this as beta plus one to n of ci ui. Have this denominator. And I'm going to be using this representation to talk about the properties of this Iv estimator. So notice I'm going to write square root n beta hat minus beta as the ratio of two things. On top we have 1 over square root n because we put the square root n here of the sum of zu. This is the same that I had in the previous slide. And then I'm going to replace x in the denominator. Remember that x here was pi z plus b. So I'm going to replace x by that. And so the denominator becomes this like average of c squared pi times the average of z times b. And I want to know by c bar squared this average of c squared moving forward. But first, notice that then I can say that the distribution, the finite sample distribution of the Iv estimator, okay, recenter and rescale, equals the ratio of two random variables. There are W1 and W2 here in the notation. Doesn't matter. I'm just labeling them. And so the joint distribution of these two random variables is normal. And W1 has mean 0. W2 has mean z bar squared pi. And they have a variance covariance matrix. Which importantly, you see that some of these terms have no 1 over n or 1 over square root n. Some have 1 over square root n. And some have 1 over n, like this one over here that is going to pop up later. And again, the notation here is that this z bar is just the average of the z's that are non-stochastic in our setting. So that's why they appear here on the right-hand side. So this joint distribution, this one over here, completely determines the finite sample distribution of the Iv estimator. Okay? And in particular, it is the ratio of two correlated normal random variables, W1 and W2. So assume for a second now that this average that we're having converges to some number. Let's call it c bar squared as n goes to infinity. Then you have that asymptotic normality will give us this result where this object that we had in the previous slide converges in distribution to a normal with mean 0 and variance equal to sigma squared u divided by this component that we have over here pretty much. And so, And so what this is doing, if you look, is like this is the mean of the random variable W2 that we had before. And this is the term that determines the variance. And so we know that 1 over n, the sum from 1 to n of zi bi converges in probability to the expectation of zb, which happens to be 0 under the assumptions that we had. So what this limiting normal argument is doing, what I wrote here, is effectively treating the denominator like a constant. It's just keeping this component, this first part is a constant, the mean, and then it's just treating all the part that gives you variability, that makes this denominator random, is treating it as 0. So you have a random denominator, and the asymptotic normality is telling you like, well, we're going to ignore the randomness in the denominator because it's supposedly going away with this. So then when is this going to be a good approximation? It is going to be a good approximation when the mean here is large relative to the standard deviation. You're treating the denominator as a constant. It has to be mean, is well defined relative to the variability that you have around it. And so that's exactly this inequality. The mean is greater than the standard deviation, 1 over square root n, the square root of this z tilde, sigma square b. So where is this coming from? Coming from this component that we have here on the variance of this W2, right? So the standard deviation is a square root of that. And if you just rearrange this, you're just saying, well, this approximation is going to work well when pi is big enough. And big enough depends on some features of the DGP, the variance of B, and this z bar square, and the sample size, 1 over square root n. So it's going to be a poor approximation when pi is small. This inequality holds in the other way. Okay. And notice that in particular, pi 0, or asking that pi is different than 0, is not sufficient for the approximation to be good. So if you just write, I don't know, let's write here a line, pi. Here we have 1 over square root n divided by the square root of Rn, this term, and this is 0. Then any pi that fits here, any pi that falls here, is problematic. Of course, in this characterization that I'm giving, pi is a constant, okay? So, but I'm just saying, what does it mean for pi to be small? Well, it depends on the DGP and the sample size. And if your DGP is such that it has a small pi, meaning that it fits or it falls into this area, then you're in a situation in which the normal approximation is going to be poor. Okay, so here we have, it's a simulation, but it shows you one thing. Like, hopefully it'll give you a clear sense of what's going on. This dotted line here is a case where pi is large. And here you have a case where pi is small. Do you see that when pi is large, and this is a case where we expect the normal approximation to be good, well, the finite sample distribution, these are plots of the finite sample distribution of square root n, beta hat minus beta. The finite sample distribution looks like standard normal. It's centered at 0, and it has the tails that are as expected in the case of a normal distribution. Whereas when pi is really small, and is one of these cases in which we say that the distribution, finite sample distribution, is not well approximated by the standard normal, you see that the distribution is not even centered at 0. This case just centered at 1, okay? And then you have some intermediate cases of values that are larger, but they are still small, okay? Like the green one or the red one, where, not only the distribution is not centered at the right place, it also, you can see that it's asymmetric. It's not, it has a longer tail in this case to the left. And, it depends on the DGP, whether pi is positive or negative or whatever, whether, this is going to be more centered, more skewed, and so on. But the main takeaway is that whenever this coefficient pi, or whenever relation between the instrument and the endogenous variable is not large enough, okay, then the approximation is poor. And notice that this is not something that gets solved by having a large sample size, okay? So you can say, well, if I have a larger sample size, I should be fine. Well, not really, because if you just look at this thing over here, you're going to see that there's always going to be, for any sample size, some area, okay, that is going to be problematic, okay? And depending on your sample size, what problematic is. But problematic is always um, possible. Anyway. So it's always possible for any sample size to have some DGP that could be problematic. And those are the DGPs that we're going to label as weak instruments. All right. So suppose that you believe me or you're convinced by this argument and you say, okay, so suppose that I'm concerned about the possibility my instruments are weak. I suspect that that's the case. And so I know that the asymptotically normal confidence intervals or confidence intervals based on the asymptotic normal approximation are not going to work. What can I do instead? Well, you can consider an idea like the one in this slide. So suppose that you want to test whether beta is equal to C or not. Okay, the alternative is beta is not equal to C. Let's just take C equal to 1 for simplicity. Okay, so then under the null hypothesis, you can compute U, which is Y equals Y minus X prime beta, and Z times U, which is Z times Y minus X beta, by replacing B with the null hypothesis. Here would be C, because you know C. We're testing beta is equal to 1, just put in 1. This is a vector, right? So it could be a vector of constants, but we're just testing that this vector beta is equal to some other vector C. Just plug in C, and now you know all the pieces. You know C, Z. I shouldn't be using the letter C and Z in the same slides because I'm really bad at distinguishing the sound of these two. But anyway, keep going. You know C, and then you know Y, and you know X, and you know Z here, so you can just compute these objects. And we also know that the expected value of CU is 0 because Z is assumed to be exogenous. So what we can say is that we can test the null hypothesis that the mean of this random variable is 0 by using Z1 times U1 times ... Zn Un, the sample that we have. How you can formalize this? Well, let Wi be defined as this different. This is an object that is well defined under the null hypothesis. And under the null hypothesis, the scale average of this W, 1 over square root n sum of W blah blah blah, converges to a normal with mean 0 and variance sigma. Okay? So where sigma here is just the variance of the W. So we can define an estimator of this sigma as sigma hat. It's just the sample variance of this guy, which is 1 over n, the sum, Wi minus W bar, Wi minus W bar prime. And then you can construct a type of wall test statistic by taking the quadratic form of our vector of means, W bar, weighted by the inverse of sigma. And by the results that we know from previous classes, since this guy is asymptotically normal, then this wall type test statistic will be asymptotically chi-squares with L plus 1 degrees of freedom under the null hypothesis, all this. So we can test the null hypothesis by comparing this test statistic with the quantile of a norm. And notice that nowhere in this derivation I use the rank of X is the correlation between exogenous variable at all. And that's why this derivation and this way of testing this null hypothesis does not depend on whether the instrument is strong or not. Note also that this way of testing this null hypothesis does not need an estimator. So it's not that we're estimating beta and then doing the test. We're just doing the test here without estimating beta. Because at the end of the day, we have a good estimator of beta, so which is our Iv estimator. This is not a bad estimator of beta. It is actually consistent. Okay. But the problem is that this estimator doesn't have a finite sample distribution that is well approximated by a normal distribution. So it's not that the estimator is bad per se. So then what you do is to supplement the inference with an approach that allows you to test the hypothesis you may care about or construct a confidence interval by doing the so-called here test inversion, or by following this approach that does not require or does not use at any point the correlation between the. Now, this idea is essentially the idea of a test, famous test proposed by Anderson-Rubin. I wrote here, a closely related variant of this idea leads to the Anderson-Rubin test, in which one tests whether all the coefficients in a regression of y on y minus x prime z on z are 0 or not. So it is mechanically similar to what I said. It involves some additional algebra here, but it's conceptually the same thing. This test has good power properties when the model is exactly identified, but maybe less desirable when the model is over-identified. Have more instruments than endogenous variables, but there's a massive literature on weak instruments and inference with weak IVs that leads to a variety of methods that some will have better power properties, some will be more appropriate when you don't care about inference on the entire vector beta, or but perhaps some components only, and so on. And so I wrote here, this literature is large, okay, and it's mostly based on test inversion, okay, meaning if you're just gonna do a confidence interval, you have to do this approach that we described in the second lecture, where you just collect all the values in the null hypothesis that are not rejected, and then you put them in back. So an alternative way would be to do a two-step approach, which in the first step, you should investigate or you can test whether the rank of this matrix is close to being deficient or the full rank or not. And then in the second stage, you just proceed in the following way. If you have evidence that your instrument is strong, just go and do two-stage least squares with an asymptotic normal approximation. You're good to go. If you have evidence that the instrument is weak, then you just then go and use one of these more sophisticated methods, Anderson-Rubin, or any of the methods that I'm describing here, that I'm saying that it exists, but I'm not describing. However, these two-step method will also behave poorly in finite sample, and is not something that I would recommend to do. Because as a general rule, whenever you follow an approach in which you have a first stage in which you test for something, okay, using a test that has the probability of making mistakes, and then depending on the outcome of the test, you decide to do A or B, okay, the end result that you're going to have, the final inference approach, is typically going to be going to deviate from the usual approximations that we use. That's not a topic that I'm going to cover in this class. It has to do with pretesting and uniform inference and so on. But the sort of like moral that I want you to remember is that anytime you just do this pretesting approach where you first test for something and then you decide to do A or B, is generally going to have poor finite sample properties. If you want to do more, you can learn those topics in 481. All right. Any questions about this? All right. So let's keep moving then. Now we got to the last part of today's class, which is about the interpretation of the Iv estimate under heterogeneity. So I wrote here, despite possible inefficiencies, two-stage least squares remains popular. So what I mean by this is something that we're going to discuss next class, which is today we show that the two-stage least squares estimator was efficient under, I call it strong assumptions, in particular homoscedasticity assumptions. And once you remove those assumptions and consider a more general model, it turns out that two-stage least squares are no longer efficient. The efficient estimator is going to be some other estimator that we're going to discuss next week. But despite this, as I wrote, two-stage least squares is still popular. And so one reason could be simplicity. And another reason that we're going to suggest today is that it has clean interpretation in the presence of heterogeneous effects. Right? I mean, it's clean in a very stylized setting, that in the stylized setting that I'm going to discuss today, which is the one that appeared in the original paper. But it's simple but popular enough case that matters. Okay, but the minute that we deviate from this, nice simple setting, interpretation is arguably less clean. But I'm not going to talk about that today. We discussed that in 41. So recall that the model that we wrote is y equals x beta times u. And then if you care about the effect of a change in x, let's consider unit change. So say 1 to 2, then the effect is the same for everybody. And in fact, it is equal to beta. That's what the linear model with constant coefficients is telling you. But what if the effect of a change in x on y is different for different people? And then, you write something like this in the abstract and it looks like it's just, you're just making the model more complicated because you want to make the model complicated. But actually, if you just think about, we're talking about COVID in a previous question. So suppose that you care about the effect of a vaccine, which is X here, on the hospitalization or the odds that you go to the hospital if you get infected, or or the odds of getting COVID, whatever the outcome it is. So now you can imagine, and we know by now, hopefully you will agree with me that different people react to the vaccine in different ways, and it could be based on things that we observe, like age. There are like good differences. Somebody who's really young or somebody who's old, but there are also unobservable differences. But if you just put all these things together, then you get to the situation which that given the vaccine to one individual or not is going to affect the odds of like getting COVID or going to the hospital or dying in different ways. So the effects, are heterogeneous. So how do you capture this? Well, one way to capture this is to allow this beta over here to be random. And when beta is random, you don't need this u anymore because you can put it as part of the constant beta naught. And so you typically write down the model like y equals x prime beta. Okay. And so the notation here means that if you just index the individuals by I, because you have a sample, say, of n individuals, then yi will be equal to x prime I times beta I. And then, it makes it explicit here that each individual will have a unique effect, beta I. So now instead of having one unique parameter beta, we're going to have n parameters, beta 1, dot, 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 beta n. Okay. So as I said earlier, I want to consider a stylized case, simple case, that it is the model case to study the questions that we're going to study today. So I'm not simplifying just for the sake of this class. As I said, is the original model that people typically have in mind. They start thinking about interpretation of two-stage least squares and under heterogeneity. So we're going to assume that we have only one endogenous variable here. Remember this partition we did before where x was x0 and x1. Well, x0 is just a constant. x1, I wanted to know here by d, just because in this literature it's very common to use the letter d. Is the letter we usually use for treatments, okay? Not only that, I'm going to assume this d is binary, okay? It's whether you took a drug or not. It's just a binary treatment, okay? And then write in the model, again, using these random coefficients, okay? We're going to have y is beta 0 plus beta 1 times d. And then beta 0 here is going to be y0. Beta 1 is going to be y1 minus y0, where this y1 and y0 are the so-called potential or counterfactual outcomes that we described before. All right, so y0 is the value of the outcome that would have been observed if possibly counterfact. D were set to 0. And y1 is the value of the outcome that would have been observed if possibly counterfact. D were set to 1. Okay? And so here we have that the observed y, the y that we observe is just y1 when people are treated and y0 when people are not treated. Just rearrange this and then you can write it like this. And then here we have that this is beta 0. So this model at top is the same as this one over here, just different ways of writing the same thing. The variable d is typically called a treatment, as I said before, and y1 minus y0 is what we call the treatment effect. It's what captures, what's the change in outcomes by receiving the treatment or not for a given individual. Now, the quantity expected value of this is usually the average treatment effect, which we described before as typically viewed as a causal parameter because it's a feature of the treatment effect, which is a random variable. So, in particular, it's the average of the treatment. So, let's start with the case where there's random assignment. So, D is randomly assigned, for example, in the context of an experiment in which you just flip a coin to assign people to treatment and control. And in that setting, you have that the treatment is independent of the potential outcomes by virtue of how we are assigning the treatment exogenously. And so, as we saw before in class or in your homework, under Mile assumption, the slope coefficient from OLS regression of y on a constant ND yields a consistent estimate of the average treatment effect. Another word to paraphrase this is to say that the OLS estimate is the average treatment effect. Let's see that. The OLS estimate is the covariance of y and d divided by the variance of d. Then in your homework, you show that this is expected value of y given d equals 1 minus the expected value of y given d equals 0. And then when d equals 1, y is just y1. And when d equals 0, y is just y0. But then remember that d is independent of the potential outcomes. So this conditioning doesn't accomplish anything. So this is just the expected value of y1 minus y0, which is the AT. So in other words, when the treatment is exogenous in this sense, then the OLS estimate, what OLS is estimating, is precisely the average treatment effect. Okay, so now in most cases, D is not going to be exogenous as in the previous slide, but rather there's going to be selection. Okay, we would expect that in many settings, people will choose D as a function of their potential outcomes. For example, if you think about, again, we keep going with the example where you're taking D as a drug, okay, that is supposedly affecting your health, which is given by captured by your outcome, okay. You may be somebody that is more willing to take the drug, having D equals to 1, when your Y0 is high, if there's a measure of risk. For example, dying, okay? If the probability that you die is really high, you know that, you may be willing to take D equals to 1, take a new medication, even if that medication, for example, could have side effects. Whereas somebody who has a low value of Y0 is just, healthy person that is not facing much risk without the medication, may be less willing to set D equal to 1. And then depending on the applications, you can find different stories. But in general, whenever D is a choice, you would imagine that people take into account their potential outcomes where they make the choice. And so in those cases, we would expect D to depend on the potential outcomes. When this happens, then the squares, OLS, will not yet yield a consistent estimate of the average treatment effect. That derivation that we did in the previous slide clearly exploited this exogeneity of D in this step. And if we can't do that, then this derivation doesn't go through. And so in these cases, since we're essentially saying here that D is endogenous, then we typically, to deal with endogeneity, we come up with an instrument. And so we're going to assume that now. We're going to have an instrument that I'm going to denote by Z. And again, the instrument here is just going to be binary. And the question that we're going to try to answer is, okay, suppose that we have an instrument, and given that we know what the Iv two-stage least squares estimate is, which is this object over here, um, can we interpret this estimate as some feature of the treatment effect? In other words, can this expression be expressed as a function of y1 minus y0, the treatment effect? Maybe some weighted average of treatment effect, or the treatment effect for some group of individuals, and so on. And so what we're going to do is try to claim that the answer to that question is yes. The goal is to express this quantity in terms of the treatment effect somehow. And we're going to do so by working out the expressions of the numerator here and the denominator separately. By manipulating this and this, we're going to be able to show that the Iv estimate is actually a parameter that is a particular average of the treatment effects. So, to do so, we need to introduce a few assumptions and a little bit of additional notation. This is the last piece of notation now, at least. So we're going to introduce the following equation for D that will bring the so-called potential treatments. So D is now, we're going to view this as the function of D. D is the decision, the treatment, C is the instrument. And so D is going to be D1 if you get the instrument equal to 1, and it's going to be D0 if the instrument is 0. And if you rearrange, okay, you're going to have something that looks quite similar to what we had before for the outcome equation. So we're just doing the same. These D's are called potential or counterfactual treatments. Some people actually just call them potential outcomes. I would like to just call them differently so that we don't get confused. But that's some people do that. And then in terms of, the model that we get is, again, another model with random coefficients here because, pi 0 is D0, pi 1 is D1 minus D0. And since we have an instrument, we typically need the conditions for the instrument to work that are exogeneity and relevance. Here, exogeneity takes this form where the instrument is independent of all the potential outcomes and all the treatments, okay? So this is stronger than some conditional mean dependence assumptions that we use in the linear model, but it is the type of assumptions that we need when we deal with a model that allows for heterogeneity. It's a more general model. And then relevance means that at least there are some people that are affected by this instrument. Some people that will make a different choice if you give them the instrument than if you don't. And so the probability that D1 is different than D0, which in other words is the same as the probability that pi 1 is different than 0, is positive. Remember that in the linear IV case, we just simply say pi 1 is different than 0 because it is a constant. But now it is no longer a constant. Relevant means that the probability that this is not 0 is positive. And that's it about exogeneity and relevance. But in this setting, we're going to be needing a new assumption that is called monotonicity. And monotonicity says that those people that are affected by the instrument, this is over here, are affected only in one direction. Meaning, when pi is different than 0, pi is greater than or equal to 0. You can do it the other way. You can go pi less than or equal to 0. Nothing changes. These are labels. But what matters is that pi is not allowed to be positive and negative. It just has one sign. And we're going to discuss what's the implication of this. This is not like a trivial assumption, okay, or innocuous. It's going to have bite in some applications. In some other applications, it's going to hold by construction, and we're going to discuss that. So it depends on the setting, how important, how meaningful this condition is, but it is essential for the argument that we're going to make in the slide. So what we're doing now, going back to our goal, we're going to take this numerator, this denominator, work it out, exploiting these assumptions that we have over here to get an expression of the Iv estimate as a function of the potential outcomes. So let's do that. I'm going to start with a numerator. So the numerator is expected value of y given z equals 1 minus expected value of y given z equals 0. This we can write by replacing y as y1 times d1 plus 1 minus d1 y0 conditional on z equal to 1 minus expected value of y1 d0 plus 1 minus d0 y0 conditional on z equal to 0. And then here I'm going to use independence of the instrument, meaning z is independent of all these potential outcomes, so the conditioning doesn't play any role. And then we're going to have expected value of y1 d1 plus 1 minus 1 y0 minus the same thing with the d0s here. And then if you group the terms together, just adding and subtracting, you get that this is equal to this. And then by the law of its expectations, this is expected value of y1 minus y0 conditional on d1 greater than d0 times the probability d1 d0. And that's the numerator. Now the denominator is actually simpler. It's expected value of d conditional on z equals 1 minus expected value of d conditional on z equals 0. And this is expected value when z equals 1, then this is d1. When d equals 0, this is d0. By independence, this is just expected value of d1 minus d0, which is just equals to the probability d1 is greater than d0. By the way, I didn't say that, but in this step over here, we used monotonicity. Because we have this term over here, and this term could be, in principle, could be 1 when d1 is greater than d0, as here. Could be 0, which doesn't matter because if it's 0, it kills everything. Or it could be -1, where this is 0 and this is 1. But our monotonicity assumption tells us that -1 can never happen. So all can happen is this over here. And the same thing for this term here. It's just equal to this probability because of monotonicity. So now you just put everything together, and then we have that the Iv estimate for the covariance of yz divided by the covariance of dz is equal to, on top, the expected value of y1, y0 conditional on d1 greater than d0, times the probability d1 is greater than d0 divided by the probability d1 is greater than d0. Voila! This guy and this guy cancels out, and we obtain that the Iv estimate equals the expected value of y1 minus y0 additional on d1 greater. So this is an average here of the treatment effect local. So this parameter here on the right is a function of the potential outcome. It's a particular type of average of potential outcome. It's the average of the potential outcome for those individuals that are affected by the instrument, those individuals that changed their decision because they got the instrument. This over here are going to be called the compliers. In the next slide, we're going to define them. But the goal of expressing the Iv estimate as a function of the potential outcomes was accomplished. This parameter over here is called the late or local average treatment effect. This is what we just proved. The Iv estimate is equal to the late effective value of the treatment effect for the compliers, which makes it local average treatment effect. Average treatment effect among the subpopulation of people for whom a change in the value of the instrument switched them from being non-treated to treated, so-called compliers. So it turns out that you can conceptually think about this population of individuals into four groups. First group would be those that have d1 equal to 1 and d0 equal to 1. These are people that, take up the treatment, say the drug, regardless of whether you offer them the drug or not, regardless of whether the instrument is one or not. So you call this always takers. Then you can think about the other guys that have d1 equal to 0, d0 equal to 0. So these are individuals that never take up the treatment, regardless of whether you offer them something or not, the instrument, offer them the instrument or not, or in the case of the drug, whether they never take the drug, regardless of whether you offer them the drug or not. So these are called the never takers. Then you have these guys that we're using here, that are those that have d1 equal to 1 and d0 equal to 0. These are units that take the treatment only when your instrument is 1. That is, they take the drug whenever you offer them the drug. But if you don't offer them the drug, they just don't take it. And these are called the compliers. And now probably it wouldn't be difficult to you to see that we have a fourth group of individuals, that these are the difficult guys. Those that when you offer them the drug, they don't take it. But if you don't offer them the drug, they just go all the way to find it and take it. And let me correct this. These are called the defiers. So when you see all this, you should realize that monotonicity means there are no defiers. Monotonicity is saying this group of individuals here at the top do not exist. And as I said earlier, in some settings, assuming a condition like this is not problematic and makes sense, and you can say it's reasonable, and in some other settings, less so. Right? So you have to think about whether in the setting that you're studying, the application and the consideration, this is something that you are comfortable with. But the assumption is fundamental. You need to impose this condition that there are no defiers in order to have a clean interpretation of the Iv estimate. Because suppose that you don't, okay? So this is what is in this line. Suppose that you just allow for defiers to be there. Then when you compute this expectation that we had in the numerator of the Iv estimate, then you will have the first term, which is the one we derived, minus this second term, which is the expectation for the defiers, times the probability that you are a defier. And so then you're open for situations like this one. Suppose that there's a positive treatment effect for everybody. Everybody benefits from this treatment. Every single person has a positive treatment effect. But as you can see here, you have a negative over here. So if the effect for the compliers is outset by the effect on the defiers, okay, then you can have the Iv estimate is actually negative, okay, when there's a positive effect for everybody. Could be zero, could be positive, but there's no guarantee that the Iv is even gonna get it right. And so having weights that are not in between 0 and 1 when you just have parameters that are weighted average of treatment effects, in this case is an average of treatment effects here minus an average of a treatment effect there, makes interpretation complicated. So in order to have a clean interpretation of Iv, you need to assume that this second term is not there. And that's exactly what monotonicity is giving you. And then you may say, like, well, what's going on here? Whenever we were dealing with the linear Iv setting, we never had a problem like this. That's true because that doesn't come up in the linear Iv model, because with constant homogeneous effects where beta, okay, or where y1 minus y0, which we call beta, is just constant and is the same for everybody. Well, if that's the case, you just plug that in into the expressions that we have here on top, and what you end up with is essentially beta times pi1, or the expected value of pi1, but let's assume that that's constant as well. And that, whenever you find a zero thing or a zero coefficient, it might be because your instrument is not relevant or because beta is actually zero. Okay? Assuming that pi is not zero, that's exactly you identify the sign. The problem that we describe over here doesn't. Okay? Questions? All right. So now let me just talk briefly about the Roy model. The Roy model has been used in economics a lot because it's a model that gives you a clean representation of how people choose D in terms of utilities. Essentially, it says people are going to choose D1 if the utility of choosing 1 is greater than the utility of choosing 0. And then you're going to write that down as a function of things that you observe, in this case, say the instrument, okay, minus or plus, it doesn't matter, and another component that is the unobserved heterogeneity that is here is captured by B. Well, it turns out that monotonicity is equivalent to a Roy model with separable utility, okay, meaning separable, meaning the instrument and the unobserved heterogeneity are written like this plus that. And so just to make it simple, let's take this nu here as a linear function of z, not necessary at all for the argument, but it just simplifies things. So d here is 1 if gamma 0 plus gamma 1 z is minus b is positive and is 0 otherwise. We're going to assume without loss of generality that gamma 1 is positive because I can do the same argument with gamma 1 negative. And so if we just write this latent index model with potential outcomes, then d0 when you set is equal to 0 is just, the indicator that b is less than gamma naught. And then d1 is the indicator that b is less than gamma naught plus gamma 1. And so you can see that monotonicity is automatically satisfied here. And so here, in the context of Roy models, monotonicity happens anytime that you consider a setting in which the utility is separable. Okay? And this has been worked out, papers by Ed Vidlasil, papers by Heckman and Vidlasil, whereas the late that I said before, almost exactly as I presented it, was worked out by Angrist. Okay? So at the end of the day, this is something that I discuss in 481, but there is a tight connection between a late approach and a latent index or Roy model type of approach. They're both one-to-one, just that they provide different interpretations of things. So I'm not gonna dwell into all these distinctions here in this class. I just want you to be aware that sometimes decisions like monotonicity may be easier to interpret in models like they have latent index, or if you're just working with a type of Roy model and you see no connection with stuff like or parameters like the late parameter. Well, the connection is there. You just need to read the relevant papers to learn how these connections happen. All right, we're getting to the end. I'm gonna discuss briefly monotonicity with one-sided compliance. This is experiments. The easiest way to think about it is experiment where you don't have the actual treatment available outside the experiment. So suppose you have an experiment, you randomize people into treatment and control. Those that are treated, okay, you just give them a drug that they're supposed to take, a medication, you can say, or something like that. But then in reality, some of those decide to use the medication, take the medication, some others don't. You, of course, observe here whether they do or not is not a missing data problem. But then what you have is then there's no compliance. Some people just don't follow the rules. You give them the drug, they just don't take it. But there's one-sided compliance because you are assuming, suppose that this new drug is new, is not available outside on the market. So those that are not part of the experiment, or those that are in the experiment but got assigned to control, okay, cannot go and just buy the drug somewhere else at a Walgreens or a CVS. So what happens in a case like that? What you have is that the zero, which is you know um, the decision that you have when you don't get the drug in the experiment, is just zero because you cannot have the drug where else. Whereas D1 can be 1 if you decide to comply and take the medication, and then 0 if you decide not to do it. Well, you can see that in this case, monotonicity holds automatically. It's not an assumption. It happens because D0 is 0, and then D1 can be 0, in which case this is exactly equal, or it can be 1, in which case this is strictly greater. So this inequality holds by construction. Okay? And so, but in this case, even though this is an experiment, see, where things were randomly assigned, D is a choice. And so now, like simple comparisons of treated and untreated will not give you something like, say, an average treatment effect, as we did in the case where D was randomly assigned. And so you have to be careful. So there are two common alternatives here that people may use. One is the so-called intention to treat effect. Okay. Z here, which is the instrument, is the offer of the treatment. And so you can compare just the effect of those that were offered the treatment with those that were not offered the treatment. And that's a parameter that people sometimes report. And the other option is the late parameter, which in this case is just the average treatment effect on the treated. And to see this, notice that the average treatment effect on the treated is just the expected value of y1 minus y0 conditional on d equal to 1. But if d equals to 1, then there has to be d1, which is the only one that can be equal to 1. And remember that d0 is always 0. So this is the same condition in the event d1 and d0 equal to 0. All these are the compliers. So in this case, with one-sided compliance, you have the average treatment on the treated is the late, or the other way around. Just an interpretation feature, doesn't change much about what you can do or what you can get out of this. Is that it's just a feature of the model. So one thing to conclude about this is that you can see that depending on the settings, and I'm going to repeat this as we move along, some of these parameters may be the answer to the questions that you have. And in some other setting, some of these parameters are not answering the question that you want. So And that applies even to things like the average treatment effect. It's just not a criticism to late per se. Think about the average treatment effect. Suppose that you want to study the effect of college on earnings, okay? Well, the average treatment effect is just going to be a parameter that is going to answer the policy question of whether everybody goes to college versus nobody goes to college. You're computing expected value of y1 minus y0, okay? And so on average, what's the effect of such a policy? And then in most instances, you will probably not care in particular about that policy. So that means that the average treatment effect may be interesting for other reasons, but not because of informing policy. For example, you may care about introducing a subsidy to go to college, lowering the cost of education or something like that, and how that affects income of the individuals. And so that is a different type of parameter. Of course, the same applies to late. Late identify this particular effect on the compliers and the settings in which the complier is exactly the subgroup of the population that you care about. And in other settings, that's not what you care about. This is not the actual policy that you care about. So it is important as you move forward and you start doing your own research, say if you're doing apply micro or the like, that you are always aware or pay attention as to whether the parameters that you're identifying are the ones that you really care about in your setting, as opposed to just do things because other people are doing things. You should make up your own mind. Okay, so we got to the end now. So I want to take any remaining questions now, but before we do so, just remember that next week we're going to be talking about GMM and empirical likelihood. So that's it for the day. Let's move to questions.